The illusion of stillness, silence. In the vacuum of the cosmos, silence is not merely the absence of sound. It is a disguise. To the naked eye, the universe appears static, fixed, a clockwork mechanism that has run for billions of years and will run for billions more. We look at the stars and see a map that our ancestors used for navigation. We see constancy. But this view is a grand cosmic illusion. Beneath the surface of reality, something violent is happening. It is happening right now, in the space between your eyes and this screen, and in the vast gulfs between galaxies. Space is not sitting still. It is not an empty stage where matter dances. Space itself is alive, dynamic, and it is doing something terrifying. It is stretching. For centuries, physics told us a comforting story. Gravity is the sculptor of the universe. Gravity pulls. It binds. It builds solar systems, compresses gas into stars, and anchors us to the floor. Logically, after the Big Bang launched matter outward, the collective gravity of all the stars and galaxies should be acting as a cosmic brake. The expansion of the universe should be slowing down. Everything should be trying to come back together. But in the early 20th century, the astronomer Edwin Hubble shattered that comfort. He peered into the Hooker telescope and saw that the light from distant galaxies was shifting toward the red end of the spectrum. They weren't just moving, they were rushing away from us. And the farther away they were, the faster they fled. This was the first tremor of the truth. The galaxies aren't flying through space like rockets. The space between them is being manufactured. Every second, millions of cubic kilometers of new nothingness are birthed into existence, pushing the islands of matter apart. We are not drifting in a static ocean. The ocean itself is growing, and for decades, we thought we understood the rate of this growth. We thought gravity was fighting a losing, but valiant battle to slow it down. We were wrong. The accelerator. 1998. Two independent teams of astronomers set out to measure how much the universe's expansion was slowing down. Their plan was simple: locate type Ia supernovae. Exploding white dwarf stars that burn with such a specific, consistent brightness that they serve as standard candles for calculating cosmic distance. By measuring how bright these explosions appeared and how fast they were receding, they could calculate the deceleration of the cosmos. They expected to see the effects of gravity reigning in the expansion. They expected a dying momentum. Instead, the data returned a result so impossible that both teams assumed their equipment was broken. The supernovae were dimmer than they should have been. They were farther away than the math allowed. The universe wasn't slowing down. It wasn't even cruising at a steady speed. It was speeding up. Someone, or something, had stepped on the gas. This discovery upended physics. It demanded a new variable in the equation of reality. If gravity pulls inward, there must be a counterforce pushing outward. A force distinct from the initial explosive energy of the Big Bang. A force that doesn't dilute as space expands, but maintains its density, gaining strength as the universe grows larger. We gave it a name that acts as a placeholder for our ignorance: dark energy. Dark energy is not a rare substance found in the corners of the cosmos. It is the dominant constituent of reality. When we tally up the mass energy budget of the universe, atoms, the stuff making up you, me, the Earth, the Sun, and every visible star, account for less than 5%. Dark matter adds another 27%. The rest? Roughly 68% of the universe is this mysterious, repulsive energy inherent to the vacuum of space itself. Think of the implication. The majority of our universe is made of something we cannot see, cannot touch, and do not understand. And its sole observable function is to destroy structure. It is the silent antagonist to gravity. While gravity tries to build galaxies and solar systems, dark energy is quietly, relentlessly trying to isolate them. For billions of years, gravity held the upper hand in the dense, early universe. But about 5 billion years ago, as the cosmos spread out, matter became too dilute. The balance tipped. Dark energy took control, and it has never let go since. The vacuum catastrophe. To understand why the universe is tearing itself apart, we must redefine what we mean by nothing. If you take a box and remove every atom, every photon of light, and shield it from all radiation, you might think the inside is empty. You would be wrong. According to quantum mechanics, empty space is a seething, boiling cauldron of activity. Virtual particles pop into existence and annihilate one another in fleeting moments, borrowing energy from the vacuum and paying it back. This activity creates a pressure, an intrinsic energy density built into the very fabric of space-time. Einstein saw this possibility decades ago. He called it the cosmological constant, a fudge factor he added to his equations to keep the universe static. He later called it his biggest blunder. But with the discovery of acceleration, physicists realized Einstein's blunder was actually a prophecy. The energy of empty space is the engine of expansion. As the universe gets bigger, it creates more space. More space means more vacuum energy. More vacuum energy pushes the universe to expand even faster. It is a runaway feedback loop of cosmic proportions. But here lies the most embarrassing problem in the history of physics. When theoretical physicists calculate how much energy should be in the vacuum based on quantum mechanics, they get a colossal number. When astronomers measure how much dark energy is actually pushing the universe apart, they get a number that is smaller by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in all of science. If the theoretical amount of vacuum energy were real, the universe would have ripped itself apart microseconds after the Big Bang. Atoms would never have formed. You would not exist. Yet, here we are. The energy is there, but it is inexplicably weak. Just strong enough to push galaxies apart, but not strong enough to shred atoms, yet. We are living in a universe that exists on a knife edge of improbability. The great erasure. We live in a golden age of astronomy. We are privileged. We can look out and see the history of the cosmos, from the first stars to the structure of the cosmic web. But this view is temporary. The accelerating expansion of space is not just moving things away. It is creating a horizon beyond which we can never see. There is a boundary called the cosmic event horizon. As space stretches, distant galaxies recede from us faster than the speed of light. The light they emit today will never reach us. They are being severed from our causal reality. Every second you have been watching this, a portion of the universe has crossed that line and disappeared from our reach forever. Imagine a civilization arising 100 billion years from now. By then, dark energy will have pushed all other galaxies so far away that their light can no longer traverse the gap. The Milky Way, by then merged with Andromeda, will appear to be the entire universe. Those future astronomers will look up and see a static, lonely island of stars in an infinite void. They will have no way of knowing the Big Bang ever happened. The evidence, the receding galaxies, the cosmic background radiation, will have been stretched into silence. They will construct a physics that describes a lonely, eternal, and static universe. They will be wrong, and they will have no way of knowing it. We are the only ones who will ever know the truth of a crowded, dynamic cosmos. We are witnessing the last clear view before the curtains close. But the darkness is not done with us yet. If dark energy remains constant, we face a lonely future. But there is a darker possibility. If the density of this energy increases over time, even slightly, it won't just push galaxies away. It will come for us. It will come for the solar system. It will come for the atoms in your body. The phantom scenario. Most cosmologists assume dark energy is constant, a steady, gentle push. But what if it isn't? What if it's getting stronger? This is the nightmare scenario known as the Big Rip. In this model, dark energy evolves into something physicists call phantom energy. If phantom energy exists, the expansion of the universe will eventually overcome the forces of gravity entirely. First, it will peel away the galaxies from their clusters. Then, it will invade the galaxies themselves. The Milky Way will not merge with Andromeda. It will be shredded. Stars will be stripped from the galactic core, sent drifting into isolation. But the horror does not stop at the galactic scale. As the expansion accelerates toward infinity, it pierces the sanctity of the solar system. The gravitational bond between the Earth and the Sun will snap. The Earth will drift into a cold, dark eternal winter. But even then, the destruction is not finished. Shutterstock Explore. In the final hours of the universe, the expansion becomes stronger than the electromagnetic force holding matter together. Planets will burst. Mountains will dissolve. Then, the phantom force will come for the atoms themselves. It pulls electrons from their orbits. It shatters the atomic nuclei. In the final fraction of a second, the fabric of space-time itself is ripped asunder. The laws of physics break down. Time stops. The universe ends not with a whimper, but with the violent unspooling of reality itself. This is the Big Rip. And while it is currently a minority theory, the data does not yet rule it out. The long freeze. However, the most likely fate is not a rip, but a fade. If dark energy remains constant, as it has for billions of years, we face the big freeze. The universe will not tear itself apart. It will simply grow too big, too cold, and too old to sustain life.
Stars will burn through their fuel and die. The gas needed to make new stars will be exhausted. One by one, the lights of the universe will go out. Galaxies will turn into graveyards of black holes and stellar remnants. And then, even the black holes will evaporate, leaking their energy away over unimaginable eons through Hawking radiation. We are heading toward a state of maximum entropy, a universe of perfect, cold uniformity where nothing ever happens again. No energy flows, no time passes, just an eternal, frozen midnight. It is a bleak ending to such a violent, beautiful story. But this terrifies us only because we are creatures of the present. We are obsessed with duration, with forever. But the universe does not owe us eternity. The fact that we are here now, in the brief, hospitable, stelliferous era, the age of stars, is a statistical miracle. We exist in the tiny window between the violent birth of the cosmos and its cold, lonely death. We are the universe's way of knowing itself before it goes to sleep. The silence of space is pulling us apart, yes. It is dismantling the stage. But for this brief, shining moment, the play is still going on. We are here. We can see the stars. We can ask the questions. And perhaps in the face of an infinite void, that is enough.